Dear friends, myself Harshavardhan, Assistant Professor of Mathematics. In this session, we are going to discuss Taylor's theorem and Maclaurin's theorem. Here, the learning objectives are statement and proof of Taylor's theorem, statement and proof of Maclaurin's theorem. Now, I am going to state the Taylor's theorem or generalized mean value theorem. Let f of x be a function defined on closed interval ab such that fn minus 1 of x is continuous in closed interval ab. That is, the first n minus 1th order derivatives are continuous in closed interval ab. Fn minus 1 of x is differentiable in open interval ab. Then there exists one real number c belongs to open interval ab such that f of b equals to f of a plus b minus a by 1 factorial into f1 of a plus b minus a whole square by 2 factorial into f2 of a plus b minus a whole cube by 3 factorial into f3 of a plus so on plus b minus a whole power n minus 1 divided by n minus 1 factorial into fn minus 1 of a plus b minus a whole power n divided by n factorial into fn of c, where f1 of a is the first order derivative of the function at x equals to a, f2 of a is the second order derivative of the function at x equals to a, f3 of a is the third order derivative of the function at x equals to a. In general, fn minus 1 of a is the n minus 1th order derivative of the function at x equals to a, and fn of c is the nth order derivative of the function at x equals to c. Now we are going to prove the Taylor's theorem. Since the given fn minus 1 of x is continuous on closed interval ab means f of x, f1 of x, f2 of x, etc. fn minus 1 of x are defined and continuous on closed interval ab. Now we define a function capital letter f of x equals to f of b minus f of x minus b minus x divided by 1 factorial into f1 of x plus b minus x whole square by 2 factorial into f2 of x plus b minus x whole cube by 3 factorial into f3 of x plus so on plus b minus x whole power n minus 1 divided by n minus 1 factorial into fn minus 1 of x minus r into b minus x whole power n divided by n factorial on closed interval ab. Call it as equation number 1, where capital letter R is a constant to be determined so that f of a equals to 0. Clearly f of a equals to f of b, because if you put x equals to b in the given equation, we get f of b is also equals to 0, because put x equals to b here, f of b minus f of b, these two gets cancelled, minus b minus b, which is nothing but 0, 0 into f dash of x is 0, b minus again b, which is equals to 0 square by 2 factorial into f2 of x, which is equals to 0, this value becomes 0, this value becomes 0, like that capital letter f of b equals to 0. That is, f of b minus f of a minus b minus a into f1 of a plus b minus a whole square by 2 factorial into f2 of a plus b minus a whole cube by 3 factorial into f3 of a plus so on plus b minus a whole power n minus 1 divided by n minus 1 factorial into fn minus 1 of a minus r into b minus a whole power n divided by n factorial. Call it as equation number 2. Given the function f of x is continuous on closed interval ab and differentiable on open interval ab, therefore capital letter f of x is continuous on closed interval ab and differentiable on open interval ab. Also f of a equals to f of b. Therefore capital letter f of x satisfies all the conditions of Rolle's theorem on closed interval ab. Therefore there exists at least one real number C belongs to open interval AB such that f dash of C equals to 0. Call it as equation number 3. Therefore, from equation 1, capital letter f of x equals to f of b minus f of x minus b minus x divided by 1 factorial into f1 of x plus b minus x whole square by 2 factorial into f2 of x plus b minus 3 whole cube by 3 factorial into f3 of x plus so on plus b minus x whole power n minus 1 divided by n minus 1 factorial into fn minus 1 of x minus r into b minus x whole power n divided by n factorial. Differentiate f of x with respect to x, we get capital letter f dash of x equals to f of b is a constant, differentiation is 0, minus the differentiation of f of x is f dash of x, minus is there, keep as it is. Here we use product rule, first function into second function. Here the first function is b minus x divided by 1 factorial, second function is f dash of x. Minus is there, minus of, keep b minus x divided by 1 factorial as it is, differentiation of f1x is f double dash of x or f2 of x, plus keep f dash of x as it is and differentiation of b minus x divided by 1 factorial is minus 1, plus into minus, minus, therefore minus f dash of x, minus, again use product rule, first function into second function. Here first function is b minus x whole square by 2 factorial, second function is f2 of x. Differentiate this, keep b minus x whole square by 2 factorial as it is, the differentiation of f2 of x is f triple dash of x or f3 of x. Keep f double dash of x as it is, differentiation of b minus x whole square by 2 factorial is b minus x power 1 into minus 1 because 2 gets cancelled, plus into minus, minus, therefore which becomes minus of b minus x f double dash of x minus so on, minus the different here, here also apply product rule, keep b minus x whole power n minus 1 divided by n minus 1 factorial as it is, differentiation of fn minus 1 of x is fn of x, minus the plus is there, plus keep b minus fn minus 1 of x as it is, differentiation of b minus x whole power n minus 1 is n minus 1 into b minus x whole power n minus 2 into minus 1, plus into minus, minus, n minus 1 is in the numerator, cancel n minus 1, in the denominator we get n minus 2 factorial because n minus 1 divided by n minus 1 factorial can be expressed as n minus 1 divided by n minus 1 into n minus 2 factorial, n minus 1 gets cancelled, n minus which becomes 1 divided by n minus 2 factorial. Therefore, this becomes n minus 2 factorial into fn minus 1 of x minus r into the differentiation of b minus x whole power n is n divided by n factorial is n into b minus x whole power n minus 1 divided by n factorial. In the numerator n is there, n cancel, n divided by n factorial equals to n divided by n into n minus 1 factorial, n gets cancelled which becomes 1 by n minus 1 factorial into minus 1 is there, after differentiation of this minus 1 is there, minus into minus plus, like this we differentiate f of x, we get this function. The terms on the RHS cancel in pairs except the last term and the last term but 2, thus we get, see here, f dash of x gets cancelled with f dash of x, b minus x f double dash of x gets cancelled with b minus x f double dash of x, like this all the terms gets cancelled except last term and the last term but 2, therefore f dash of x equals to minus of b minus x whole power n minus 1 divided by n minus 1 factorial into fn of x plus r into b minus x whole power n minus 1 divided by n minus 1 factorial. Call it as equation number 4. In equation 4, put x equals to c, we get f dash of c equals to 0. We know that by Rolle's theorem, f dash of c equals to 0. Then equation 4 becomes minus b minus x whole power n minus 1 divided by n minus 1 factorial into fn of c plus r into b minus x whole power n minus 1 divided by n minus 1 factorial, which is equals to, this is our f dash of c, which is equals to 0. R equals to, see, bring this to right side, we get r into b minus x whole power n minus 1 divided by n minus 1 factorial equals to b minus x whole power n minus 1 divided by n minus 1 factorial into fn of c. See, n minus 1 factorial, b minus x whole power n minus 1 gets cancelled. Therefore, capital letter R equals to fn of c. Substituting R value in equation 2, we get f of b equals to f of a plus b minus a into f1 of a plus b minus a whole square by 2 factorial f double dash of a plus b minus a whole cube by 3 factorial f triple dash of a plus so on plus b minus a whole power n minus 1 divided by n minus 1 factorial into fn minus 1 of a plus b minus a whole power n divided by n factorial fn of c and closed interval ab as required. This completes the proof of Taylor's theorem. Note 1. Replace b by a plus h in equation 4. Then c can be written as c equals to a plus theta h, where theta lies between open interval 0, 1, and the theorem becomes, if f of x is a function defined on closed interval a comma a plus h such that f of n minus 1 of x is continuous on closed interval a comma a plus h, fn minus 1 of x is differentiable on open interval a comma a plus h, then there exists at least one real number theta belongs to open interval 0, 1 such that f of a plus h equals to f of a plus h into f dash of a plus h square by 2 factorial into f double dash of a plus h cube by 3 factorial into f triple dash of a plus so on plus h power n minus 1 divided by n minus 1 factorial fn minus 1 of a plus h power n divided by n factorial fn of a plus theta h, where h power n divided by n factorial into fn of a plus theta h is known as Lagrange's form of remainder after n terms in the Taylor's expansion f of a plus h. Note 2. Put n equals to 1 in the Taylor's theorem, we get, that means n equals to 1, f of b equals to f of a plus b minus a into f dash of c, which implies f dash of c equals to f of b minus f of a divided by b minus a, which is the result of Lagrange's mean value theorem. Therefore, if you take n equals to 1 in Taylor's theorem, we get the Lagrange's mean value theorem. Note 3. Maclaurin's theorem. Now take a equals to 0 and b equals to x in the Taylor's theorem, we get f of x equals to f of 0 plus x into f dash of 0 plus x square by 2 factorial f double dash of 0 plus x cube by 3 factorial f triple dash of 0 plus so on plus x power n minus 1 divided by n minus 1 factorial into fn minus 1 of 0 plus x power n divided by n factorial fn of c is known as Maclaurin's theorem. Taylor's infinite series. Taylor's series of f of x about the point A is given by f of x equals to f of a plus x minus a into f dash of a plus x minus a whole square by 2 factorial into f double dash of a plus x minus a whole cube by 3 factorial into f triple dash of a plus so on x minus a whole power n minus 1 divided by n minus 1 factorial into fn minus 1 of a plus so on. The Maclaurin's infinite series. Taylor's series of f of x about the point a equals to 0 is given by f of x equals to f of 0 plus x into f dash of 0 plus x square by 2 factorial into f double dash of 0 plus x cube by 3 factorial into f triple dash of 0 plus so on plus x power n minus 1 divided by n minus 1 factorial into fn minus 1 of 0 plus so on up to infinity, which is known as Maclaurin series. The session outcome are: learn the statement and proof of Taylor's theorem and Taylor series expansion. Learn the statement and proof of Maclaurin series expansion. I referred the textbooks Differential Calculus by Shanti Narayan, P.K. Mittal, Textbook of BSc Mathematics by G.K. Ranganath, Textbook of Mathematics BSc Second Semester by Professor G.B. Gururajachar, Textbook of BSc Mathematics by B.B. Manjunath and Dr. C. Nandish Kumar. Thank you one and all.